Well, let us now discuss something about how we can develop a mathematical expression for the heat transport in the solid liquid phase transformations. As you see, this is an interface which I have drawn between the solid and liquid, and this is solid, this is liquid. The temperature gradient both in solid and liquid are positive because the slope of these curves are positive. So therefore, as the latent heat is getting released at the interface during unit step of solidification, as a one layer of liquid solidifies and joins the solid, the amount of heat which is generated will be evolved there. So if I write the growth rate as V dot means dx by dt, right, because that is what is the growth rate per unit time. If it moves dx distance, then it is dx by dt. Growth rate multiplied by the heat evolved per unit volume is what is the total heat generated because of the latent heat evolution. Thus must be equal to, or thus this plus, obviously this plus the temperature gradient in the liquid multiplied by thermal conductivity. As you know, this is the Fourier term. This must be equal to the temperature gradient in the solid multiplied by the conductivity, okay, of the solid. So KL and KS are the thermal conductivities of the liquid in the solid. So at a steady state, this must be satisfied. The heat generated plus the heat transport, heat generation rate, actually you can see this is because this is dot, plus the heat transport to the liquid, it must be equal to the heat transport to the solid. So this actually allows us to calculate what is the V dot. So V dot is Ks dTs dx minus KL dTl dx divided by minus delta H divided by L divided by V alpha. Okay. So as you clearly see, if you want to have a very high growth rate, very high growth rate here, okay, what you need? You need to have, because this term is always positive, the delta H is the heat evolved, that is why you put a heat negative sign here, but otherwise this is positive. Volume of solid, this is volume of solid, not alpha, sorry, volume of solid is also positive. So Ks dt dx is positive here, right, dt dx is positive, K is positive. Similarly dt dl, dTl by dx and KL is also positive. So therefore this, in order to maximize this, I must make dt dl as a negative, because if that is the negative, then this plus this become very high value. In that case I can make the system grow very fast. That is the reason we better to have this situation which I have shown in the book, in the slide, this situation where temperature in the liquid is negative. So the temperature in the liquid is negative, dTl dx become negative. So this negative sign and this negative sign become positive. So these plus this become very high value, and then growth rate is very high. That is the one important aspect you must understand, that this thermal heat balance tells you that if I want to make growth rate positive, very high, I must develop negative temperature gradient in the liquid. That is the first thing which you have understood. Now let us do a little bit of calculation of the density growth which I have shown you, so that we can get into some maths. I erase this part and get back to you. As you have seen, the way I have drawn the dendrites and shown you is basically looks like this. Okay, this is on a surface and no protrusion is formed. This is solid, this is liquid, it is going. So normally dendrites keep the shape same when they grow into the liquid. They do not change the shape. So therefore I can write down, when the dendrites grow, this growth actually happens in certain crystallograph directions. I can write down that this, the heat release at the, and let us suppose this is the radius of the tip of the dendrites. That is what is more important, because that is in touch with the liquid. So this is this total area, multiplied by the obviously heat flux or rate, thus must be equal to growth rate multiplied by pi r square, correct, multiplied by delta H L by V s. This is the heat evolution, correct. So, that is we can write down, and here Q dot is nothing but K L T L minus T S divided by R. That is the heat divided by the distance is what is your flux, correct. So, finally, we can actually get the V dot growth rate of the dendrites as like this. This is the heat evolution. Okay, remember this is half because half of these surfaces are only in touch with the liquid, that is why. And this is what is your flux, this is given by this, and this is the growth rate multiplied by the area multiplied by the heat which is evolved because of the latent heat. So, this gives you an idea about growth rate, that is equal to minus K L V S T L T S minus T L, this is T S minus T L divided by R multiplied by delta H L. That is what you get, correct. So, remember this V is the volume, okay, this V is not the growth rate, the V dot is what is the growth rate. So, finally, you can convert because we are basically using this term of Q and converting everything, that is why the R comes into picture. So, this is what is the maximum growth rate of a dendrite whose growth is basically dependent on the heat transport. Heat is critically transported to the liquid because liquid is undercooled, this situation is similar to this. So, liquid is liquid has a negative temperature gradient. So, heat will be basically rejected at the interface and traveling into the liquid or basically transported to the liquid because of this negative temperature gradient develop. Okay, heat can also be transported to the solid, but transport to the liquid is faster than the solid, that is what happens. Okay. And so, this is the kind of calculation one can do. As you can clearly see, if I know the temperatures, basically we know the liquid temperature very well, but the important point is knowing the temperature of the solid, that is temperature at this interface, which is very difficult to measure. The rest of the things are known, KL is known, Vs is known, okay, and your delta H is known. So, now if I carefully write it down, that then it becomes V dot R, basically the growth rate, okay, is V dot R is equal to minus twice K L V S T S minus T L divided by delta H L, correct. So, this completely depends on basically temperature difference between solid and liquid, that means this depends on the undercooling, okay, delta T. So, if I have any idea of measuring the undercooling, then I can calculate the V multiplied by R, that is the growth rate multiplied by the tip radius. But remember, both these two things are actually unknown because I do not have any idea what the tip radius is a priori. I want to know what is the V dot, what is the growth rate basically, I want to calculate. So, finally, I get down to an equation which tells me that these two are actually related to each other by a function. So, in order to obtain individual values of both these two, I need another equation, very clear, because these are coupled together, the growth rate and the tip radius are coupled together with a function, and this function can be calculated by knowing the undercooling, by knowing the volume of the solid, KL and latent heat evolved. But I cannot determine independently V dot and R, it is not possible. So, that is why you need a second equation. The second equation people normally use or normally people used to use is basically maximum growth rate criteria. That means whatever the situations at the given condition, experimental conditions, V dot will be maximum. Okay, so therefore, we can differentiate V dot with respect to temperature and find out what is the V dot values, and then from the V dot we can calculate R. But you know, most of the systems do not grow like that way. Most of the systems do not grow at the extremum or at the maximum growth conditions. So that is why this theory, which was developed much earlier, 1940s, late 1940s, 1947-48, was unsolved for a long time, because this requires another equation to be developed. And then after long time, about 30 years, some people have discovered some things which is some people have discovered that the second equation which is required to solve these uncoupled problems basically must come from the stability of the dendrites. That suppose I have a dendrite tip like this, under what condition this tip will not become like that, or under what condition this tip will not become like this. Okay, that means under what conditions tip will remain stable. So therefore, people actually use the stability conditions for the planar interface. That means under what condition a planar interface, this is a planar interface, under what condition the planar interface will become like that. Okay, and then so this condition was used to obtain the second equation for growth rate, and problem was solved. So let us not discuss much about that, because that basically requires a very big and separate discussions. But in a nutshell, this is what actually leads to the phenomenal growth of the dendritic growth theory. Now we will go back into the situation of alloys, because that is also very interesting. You know, in case of alloys, we need to discuss how not only the heat but also solid transports to the solid or liquid, okay, or basically liquid, because solid transport to the liquid solid is very slow. Now I will just start the process and let me see how much I can discuss today for that, correct. Let us do that, let me see, okay. So first let me draw a simple phase diagram. This is temperature, this is composition XB, okay, I am drawing part of it, part of the diagram. Now let us suppose I have got solidus and liquidus. So I draw solidus by a green line and I draw liquidus by a red or pink, basically pink is better. This is my liquidus. Now let us suppose that I want to solidify an alloy with a composition given XB0, okay. I have to solidify that, and this is my liquid, this is alpha, this is liquid plus alpha. This is basically part of the phase diagram like this. I am not drawing the part of that, basically a each end. Okay, so what will happen if I start cooling it down from the liquid? Suppose if I have a temperature somewhere there, I start with that. This is my liquid temperature, okay, a T let us suppose. As you see, if I cool it down till this temperature, this is what this liquidus curve is basically temperature line and liquidus curve crossover. So at temperature T1 things will start happening. Okay, at temperature T1 a solid will form whose composition is basically given by this point. Okay, let us suppose this is XB1, the solid composition. Okay, so as you cool it down a little more, because solid and liquid compositions are widely different. You can see the liquid composition is XB0 initially. Initially liquid has a composition of XB0, and the first solid which is forming out of these has a composition of XB1. So therefore solid which is formed has a much lower B XB basically than the liquid from which it has started to form. So there is a compositional difference. That means what? A solid forms because its composition is lower, so therefore whatever remnant solute which was present in the liquid because of solid formation will be rejected in the liquid. Things will be much clear if I cool, if I basically drop the temperature a little more. Suppose if I drop the temperature from T1 to T2, okay, this is my T2 temperature, this is my T1. So, at T2 temperature you can clearly see solid which will form as a composition Xb2. On the other hand, liquid which will form as a composition Xbl2, let us suppose. Okay. So, this was my first liquid composition Xbl1, you can write down, but this is equal to Xb0 because that is the starting composition of the alloy. So, therefore, I have again difference between the solid which is formed at the temperature T2 and the liquid which is present in contact with that, and this difference is what is the solute rejected in the liquid, because you cannot create mass, you cannot destroy mass. So, whatever is basically present in the system must be balanced between the solid and liquid. Say the solid has a lower composition, then the remaining solid will be rejected in the liquid, and this will keep on happening as you lower the temperature again further, you see here things will happen. So, as you clearly see here, the solid which is forming at T3, this is at T3 suppose, at T3 or at T4, solid which is formed has compositions given by these points, and liquid which is in touch with the solid has a composition given by these points. So, therefore, as this solid solidification happens, as the system is getting cooled continuously from the high temperature lower temperature, solidification will happen, and this solidification will lead to solute getting reacted to the liquid. Because of that, liquid composition will further increase. As see here, liquid composition increased from Xb0 to Xb2 to further, and solid composition also has increased from Xb1 to Xb2 to and further. But important aspect is that there is a difference between the solid and liquid compositions, and this happens in equilibrium situations. That means when you are cooling slowly, this will happen, because this is a phase diagram which is basically based on the equilibrium calculations, thermodynamic calculations using equilibrium. So, this happens. So, now that means if I want to create a solid whose composition is exactly same as the liquid starting with Xb0, I have to basically keep at every temperature at a very long time for the adjustment of the compositions, okay, because the solid and liquid which is forming at every temperature has different compositions, and these different compositions will lead to inhomogeneity in the solid. Okay. To give an idea, suppose let us suppose at T1 I have a solid which is formed. This solid has a composition of Xb1. Okay. At T2 there is another solid formed, it will be obviously forming on the surface of this Xb1 of this first one. This is a composition of Xb2. At T3 it has a composition of Xb3 suppose. Xb3 is here, Xb3 is here, and this is Xb4. Okay. So, Xb3 and then the last Xb4 I have shown you. What is happening here? Because of the solidification, nature of solidification, if we do not allow sufficient time to the system, the compositions of these solids will be varying. Xp1 is different from Xp2, then Xp3, then Xp4. So, if I draw a line from the center to the periphery will be having higher solute than the center. Periphery will have higher solute Xp4 than the center which is Xp1. So, there is a compositional gradient created from the center to the periphery, and this is widely known as coring in the literature, because you are creating a structure which is shell like. The inside one has a lower solute than the outside shell, and that is why it is called a coring. This is widely observed in the real situations, because real situations are the ones in which diffusion is very slow, and we do not have sufficient time when you are cooling down from the liquid to the solid. So, therefore, if you want to stop this, and have a uniform composition of the solid Xb0, you need to keep this solidification, keep the system at T1, T2, T3, T4 or further long time, sufficiently long time. If I keep it, then what will happen? These two layers will get homogenized, the composition of Xp1 and Xp2 will become homogenized. Similarly, composition of Xp1, Xp2, Xp3 will be homogenized at T3 if I keep it long time, and so on. and this is known as equilibrium solidification. In equilibrium, this is what is done. It is done at a slow rate. The sample is kept at the temperature of T1, T2, T3, T4 for a long time, sufficiently long time. These compositional differences are annihilated, or these composition differences are basically completely taken care of. But actual situation, normal solidification, we cannot do that. We cannot actually keep the system sufficiently long time, because in industry or even research laboratories, experiment will have a time scale, and that time scale cannot be infinity, because there is a production loss or many other things can happen. Because of that, actually the temperature is dropped from the liquid to the solid continuously, and because of this drop, this is very common. The situation of like this, where the compositional gradient develop from the center to the periphery, is very common, and it has been observed that this situation are actually there in the actual practice. So therefore, the solid will have a core structure and core structure, and because of these, the properties of the solid from the compositional variation is so much that will vary from one place to other place, and this is not desirable, and that is why this kind of solids actually are later on heat treated at higher temperatures close to solidus temperature to make the systems homogenized. That is done actually real practice. So that is one part of it. Now question is this: how I can scientifically analyze this problem knowing this aspect, that is a solute partitioning from the liquid to the solid. Okay, how we can analyze that? Well, I will do that, but let me plus define, we will continue doing that. Let me plus define a parameter known as partitioning coefficient K. Partitioning coefficient K is basically defined as composition of solid divided by composition of the liquid. That is what it is. And because liquid composition is always higher than solid, this is a fraction in such a kind of phase diagram, okay, where it is going down. This is a fraction basically. So because of that, K normally is less than 1. As you see that in a phase diagram a little bit other way, that is, the phase diagram is like that, then K can be more than 1 also. Okay, here liquid has higher composition than solid. Okay, so therefore it is always possible that, solid has higher composition than liquid, because this is solidus, this is liquidus, this is at higher than this one, so therefore K can be more than 1. But normally we encounter such a kind of phase diagrams more, so therefore we will assume in all our calculations K is less than equal to 1, less than 1 actually. So how this situation will lead to a dendritic growth and other things we will discuss in the next class in detailed manner, and show you that we can use this phase diagram data to formulate a new theory.